So today, let me just go right into stuff. Let's make a little progress. It's been a while. So we just started last time. We had uh, just watch it later on video. So I'm going to skip questions on homework today and just go back to making some progress on new stuff. And then Friday, I'll answer questions. Um, and for the people, I have not graded the notebooks yet. So if you want to take notes in your notebook, that's fine. And then just give it back to me and I'll get it back Friday. Okay. As God is my witness. Um, okay. So we started talking about, so last time was quite a while ago, but we started particle kinetics. Um, and I talked about free body diagrams. Um, and that included representing forces with unknown directions and known direction forces. And so now I want to talk like what are the cases where we know the directions of forces? And there are three of them. So three types of forces with known directions. Um, and that is pushing contact, pulling contact, and pulling contact is contact. Those aren't graded, but if you want to take notes in it, feel free. But you might want to go back, but now come back. Okay, so pulling contact either involves cables or you can replace the contact with cables. So I'm going to say usually with cables. And then the last one is friction. And so I'm just going to go through these one by one. Um, so first, pushing contact. Um, uh, Pushing contact is always perpendicular to the surface of contact. Toward the chosen body. So, for example, um, if you have two carts that are in contact, let's call the big one here A and the little one B. And let's say that this force applied to B is 500 newtons. And the wheels here, if you're in any case where you're not given like uh, radii of wheels and masses of wheels and stuff, that's really just to indicate that it's frictionless. Later, we'll talk about how to do calculations of actual wheels. Um, but for us, this is exactly the same as these two blocks just being on ice or an air hockey table or something. It's just frictionless. The free body diagram of A, there's a weight force, I'll call that MAG. And then since these are particles, we don't have to differentiate, worry about like where these forces are applied. We treat everything like it happens at the center of mass. Um, but there's a pushing contact up from the ground. And so think, what's the surface of contact? It's the ground in this case, so it's perpendicular to that. That narrows it down to two possible directions. In this case, up or down. We want up because it's toward the chosen body, and our chosen body here is A. So we'll call this normal A. Remember, anytime you know the direction of a force, you represent it as an arrow and then a scalar variable associated with it. And now we go around the boundary of body A looking for contact with the outside world, and the only other place there's contact is with B. And those two are pushing on each other. So the surface of contact is that vertical face where they're in contact. So perpendicular to that is either to the left or the right. In this case, it's to the left because it's toward the chosen body. So I'll call that R. And for body diagram of B. Oh, before I go into B, what about the 500 Newton force? Yeah. Yeah, it's applied to B. So all you're doing when you're drawing free body diagrams is applying the weight force or any other kind of field force if there's an electric field or a magnetic field or something. So you have the weight. And then just go around the boundary and look for places where the surroundings contact the boundary. No matter what happens away from the boundary, it doesn't affect that free body diagram. Okay. That 500 Newton force definitely affects the motion of these two things, but that'll, if you're careful about it and just represent the forces at the boundary, and that the effect of that 500 Newton force is going to come through that reaction force at R. Okay, so if this force goes down, and this force ends up going down, and that's how it affects the motion of body A. Okay. And then body B, we have a weight force of MBG, pushing force from the ground, perpendicular to the ground, the surface of contact, toward the chosen body, and I'll call that NA, nope, NB. And now I'm going around counterclockwise. The first place that the outside world makes contact with this is over here with that 500 Newton force. We don't know what's causing that, but it's in there. So, and then keep going around and you get to the contact with body A. And there's two ways to think about this. It's a pushing contact, so this has to be perpendicular to that vertical surface toward the chosen body. Or since this represents the exact same contact force as this R on our free body diagram for A, Newton's third law says that it's the opposite direction, same magnitude. By the way, how does this relate to the double subscript notation that we use for force vectors. Well, this r is a scalar, right? That's not a vector. So you can't use the subscript notation for this scalar r. But if you think of that scalar r and the direction combined into a single thing, okay, then this thing here, all of it combined, is the force on A by B. Okay, so if you want to talk about that whole thing as a vector, those two bits of information together, then you can represent that as the force AB. And then this over here together is the force BA. And if you calculate the components of this and the components of this, what you see is that force AB is negative force BA. And so that way of thinking of Newton's third law works too. It just doesn't work for the scalars. So what you can't do is find out this is 500 and say that means this is negative 500 because, okay, so if this is 500, you have this vector going 500 this way. Now you come over here, we've drawn a different arrow. If you think of this as negative 500, you have negative 500 times a unit vector that way, which is 500 this way. You got your sign backwards, and your thing crashes, possibly burns to the ground. Okay. The second type of force where we know the direction is pulling forces, pulling contact. Usually this will be with cables. And pulling contacts are along the line parallel to the cable. What if there's no cable? Well, pulling contact, you can always imagine replacing whatever contact it is with a cable. And so it's the direction that that cable would be, you know, parallel to the angle that that cable would be at. And second, away from the chosen body. So pushing contact is toward the chosen body, pulling contact is away from the chosen body. It makes sense just if you think about, like, so if I'm wearing like a puffy coat or whatever and someone pushes on me this way, it, you know, the material, the outer material of the coat goes towards me. You know, that's the direction of the force. Someone pulls on my shirt or whatever, the material goes away from me. Like, it's very intuitive with what those things do. And as an example, so let's say we have an object here connected to a cable, and then another cable connecting bodies A and B, and then a 300 Newton force. So a free body diagram of body A. You have the weight force, MAG. And now they're pulling contacts at two places by those two cables. The one that's attached to B is parallel to the cable. away from the chosen body. So I'll call that T1. And the cable connected to the ceiling is parallel to the cable away from the chosen body, and I'll call that T2. And then a free body diagram of B. There's the weight force, MBG. There's the given force of 300 newtons. And then there's the force applied by the cable between A and B. It's parallel to the cable, away from the chosen body. And since it's the same cable as this one that I labeled T1, magnitude is the same. When can you assume that the cable tension is constant along the length of the cable? Or what are the assumptions that we're making there? Yes, that is. And if the cable doesn't make contact with anything else in between, then that's the only one. So that's assuming that the cable is massless. Obviously, in a cable is never massless. So when would you make that assumption? When the tension forces in the cable are a lot bigger than the mass of the cable. And then also, if the cable, so this is massless cable, and then it also requires that the cable only touches massless, frictionless pulleys. Um, so those are, pretty big assumptions, impossible assumptions, except a lot of times cables are used to support forces that are much bigger than the masses of the cables, much bigger than the effects of mass on the pulleys. And pulleys are usually made with pretty low friction. So you can get pretty good results with this in a lot of cases. Later on, we'll do some calculations of, and actually, I think this is pretty interesting. We'll do some calculations where the pulleys do have mass and size, and we'll take that into account and see how that affects the cable tension along its length. Okay, so let me do one with a pulley. So there's a pulley connected to the ceiling. And let's say this is body B. And this is body A. Let's see. So if this is massless, and the pulley is massless and frictionless, First, the free body diagram of A. There's a weight force, MAG. And then the cable force is parallel to the cable away from the chosen body. I'll call that T. And now body B. The weight force is MBG. Cable force is parallel to the cable away from the chosen body. And because of the assumptions we made about masses and friction, this cable force is the same as the other one. Any questions about that? And the last case of forces where we know the direction is friction. So the direction of friction force is always parallel to the surface. And then I'm going to, how do you figure out so it's parallel to this surface, but it could be this way or that way along the surface. So how do you figure out which one of those two it is? There are two answers to that, depending on what kind of friction you're talking about. If it's kinetic friction, so in that case, we have relative sliding between two surfaces, the bottom of your object and, or, one surface of your object and one surface of the surrounding object. Then the direction is opposite the chosen body's velocity vector. So I'll call this like part one, lowercase I. And then part two is if you have static friction. This is when the objects are at rest relative to each other. In that case, the friction force is opposite the acceleration of the chosen body that would occur without friction. Okay, I think that's all I want to say about that. And now I'm going to do some examples. Also, let me say this sort of as an aside. We're not going to deal with a lot of funky joint types in this class, but in statics we had all these different types of joints that we dealt with. And so you can also get forces with known directions if you're dealing with, you know, different kinds of joints. Um, so some joints apply forces with known directions. But in this class, we're really only going to be dealing with simple joints, rollers, frictionless contact, um, and pin joints and ball and socket joints. Okay, so I already introduced Newton's second law, I think, right? I don't know. Let's get it in here. So the key thing for the key equation of motion, the one equation of motion uh, for particle kinetics. So the equation of motion governing particle kinetics is Newton's second law. I'm going to abbreviate that as N2L. And it says that if you add up all the external forces acting on your chosen body, that's equal to the mass of the chosen body times the acceleration of the center of mass of the chosen body. So F net is the sum of all external forces on the chosen body. Why don't you have to worry about any internal forces? Because of Newton's third law. M is the mass of the chosen body. And ACOM is the acceleration of the chosen body's center of mass. Um, okay, let's do a couple problems. All right, so let's say that we have a 5 kilogram box. And it's connected to a cable. And sitting on top of the 5 kilogram box is a 2 kilogram box. And it's connected to the other end of the cable as it goes over a pulley. And let's say that you apply a 50 Newton force to the 5 kilogram box. And let's say there's a coefficient of friction of between boxes of 0.2. This is going to be moving. and the coefficient of friction between the floor and the 5 kilogram box is 0.3. And we want to calculate the acceleration of this system. There's one more bit of information we need before I can calculate that. So if this is moving, what else do we need to know? So, yeah. Well, we need to know the direction of the friction force, and if they're moving, the direction depends on the velocities of those objects. And we can't calculate velocities from Newton's second law. Newton's second law only deals with accelerations. So if these things are moving, we need to know which direction they're moving at that instant. So the 5 kilogram box at this instant is moving to the right. Okay, so, and then how is that possible? Does that make sense that the 5 kilogram box is moving to the right? All you're doing is applying a force to the left. Well, it does make sense, and this is a sort of an important thing to keep in mind. We're always dealing with individual instants. And at a given instant, forces relate to acceleration. They don't relate to velocity. Velocity depends on all the accelerations up to that point. You know, it's an integral of velocities. And so this makes sense if you think about it as like up until right before this instant, you were applying a big force to the 2 kilogram box this way. Okay? Like you apply a big force to it, maybe to picture it, imagine this platform being a lot longer. So you could apply that force for a while, get it going pretty fast. Then you let go of it. The friction and everything is going to start to slow this system down maybe, but this is still going to be going that way, and so this is still going to be going that way. So just remember that at a single instant, the forces and the velocity are unrelated to each other. The velocity is only related to the forces that happened up to that point. You know what I mean? Any questions about that? Okay. Well, we jumped into kind of an ugly problem here, but let's draw the free body diagrams. So the 2 kilogram box, let's just think it through. We know there's going to be a weight force, and then we're just going to go around the boundary looking for contacts. And at each one of those contact points, we're just going to apply the rules for the force direction to figure out, where stuff goes. So there's a weight force of 2 times 9.81. So 19.62. And now at the bottom of the 2 kilogram box, it makes contact with the 5. There's a pushing contact. So that's perpendicular to the surface toward the chosen body, and I'll call that N1. And then relative to the 5 kilogram box, which way is the 2 kilogram box moving? Left. The friction force is opposite that. So there's a friction force to the right of 0.2 times N1. And now I'm going to keep going around counterclockwise, and on the next surface, I get this cable force. The cable's attached to it. That force is parallel to the cable, away from the 2 kilogram, and I'll call that magnitude T. Okay. And hopeful. Uh, maybe we can solve it already. I can't. But let's just write out Newton's second law and see if what we can figure out. So if we're using the usual coordinate system, the cable tension, the cable force is in the positive x direction, so that's T0. The friction force is in the positive x direction, so 0.2 N1, 0. Normal force is in the positive y direction, so 0 N1. Friction for weight force is in the negative y direction, 0, negative 19.62. And so that's the left side of Newton's second law, everything that's represented in free body diagram. And then that's equal to the mass times the acceleration. And one thing about rolling and sliding problems is we can always pin down the direction of acceleration to a line. Because we're assuming that it's not jumping up into the air or sinking down into the surface. And so I'm going to represent this as, we know it's moving along the x-axis. I'm going to represent it as A2, 0. Because we know that it's parallel to the x-axis. And I didn't make a distinction between whether the acceleration is going to be positive or negative. In general, like that's going to be hard to figure out intuitively. In this case, maybe it's not so hard, but the sign will work out on its own. Okay, so can we solve this? We have two equations, three variables. So no. And it makes sense that we can't solve it with this information if you think about it, because we haven't put anything in about the friction between the ground and the lower box. And intuitively, like that would definitely affect the motion of this thing. Okay, so a free body diagram of the 5 kilogram box. There's the weight force of 5 times 9.81, so 49.05. There's pushing contact and a friction force with the ground. So I'm going to call that the pushing force, I'm going to call N2. The box, the lower box is moving to the right compared to the ground. And so this friction force is this way. And the magnitude is 0.3 N2. Go counterclockwise and you get to this face, and the cable force is the same as the other cable force away from the chosen body. And then we get up to the top, and there's two ways to think about what's happening at the top. One is that this is a contact force between a 2 kilogram mass and this one. And so if you think of these two vectors added together, that's the force on 2 by 5. Okay? And so the opposite of that force vector that you get from adding those two is the force on 5 by 2. Or you can just go back and think about it as a pushing force and a friction force and think about the directions and stuff. But it is worth remembering that this is a contact force. So this is like the force on the 2 by the 5. And so we can use the same variables when we go to the 5, just have N1 pointing down and 0.2 N1 pointing to the left. So there's N1. There's 0.2 N1. And then that's everything. So Newton's second law. Yes. Otherwise it would just sit there. I guess actually since it's moving, we would see how fast it was, slowing down. But yeah, thanks. 50 newtons there. Okay, so Newton's second law says negative 50, 0 plus negative 0.2 N1, 0 plus 0, negative N1 plus T0 plus 0 N2 plus 0, negative 49.05 plus negative 0.3 N2 1, 2, let's see, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7. So that should be it. And that's equal to the mass, 5, times the acceleration of the 5 kilogram box, which again we know is in the x direction because it's sliding along the x direction. Okay, so now we have 4 equations. And how many variables? Hopefully 4. So 1, 2, 3. That's T, N1, and A2. And then N2 is 4. And then A5 is 5. We need one more equation without adding any variables. Anyone have any idea where this extra equation is going to come from? It's going to come from, well, it's going to come from what the cable and pulley sort of do to these objects. Like accelerations of those two boxes are not independent. If you pull one this way, the other one goes this way. Okay, so we're going to need one constraint equation. On the motion. And in this case, if we assume that that cable is, okay, we're already assuming that the cable is massless, the pulley is massless and frictionless. Might as well also assume that the cable is inextensible, it's already kind of ridiculous. So if the cable, not really, I mean, that's a pretty good assumption. Yeah. No, I'm not. I'm just gonna say that because that cable doesn't stretch, so if the cable is inextensible, then think physically about what happens if you move the 2 kilogram box an inch this way. Where does the 5 kilogram an inch the other way? Right? That's a 1-to-1 relationship. And so if you're moving this at 2 miles per hour this way, what does this one do? 2 miles per hour that way. And the same thing with the acceleration. So if this is moving A2 this way, I guess, and and this is moving A5 the other way. So A2 is negative A5. And so now we have 5 equations for 5 unknowns. And we can solve that. Right, they do not. That's completely just a restriction on motion variables. And that's sort of a key thing to these constraint equations. This is going to come up over and over again. Like, we'll come up with our system of equations from Newton's laws, and then we'll look at the motion and say, is there anything we can say just purely about the motion? Like requirements that we could look at the video and say, like, that has to do this, you know? Yep. Yeah, that's how I would do it. So the way to do it is set up an augmented matrix and solve using reduced row echelon form. And I think all of your calculators will do that. It's usually called RREF in your calculators. And the way it works is you set up this matrix where each row represents an equation. So that's 1, 2, 3, 4, 5. And each column represents a variable. So the variables we have are t, n1, a2, n2, and a5. And there's one column left over, and this is the constants. And these are alone on the other side of the equation. I'm not going to solve this right now. So now we're just going to put the coefficients of all these things in here. So I'll finish this on Friday. But like our first equation says T1 plus 0.2 N1 is equal to 2A2. So we can rewrite that as T plus 0.2 N1 minus 2A2 is equal to 0. Then we have, for T's, we have 1. That's the coefficient. For N1s, we have 0.2. For A2s, we have -2 because you want to get all of those on the same side of the equation. And everything else is 0. And fill out that whole thing, do reduced row echelon form, and it'll give you the answers. I'll go through it on Friday. Anybody have any questions? Okay.